All right, one more topic to talk about having to do with equilibrium is buffers. Before we get there, I want to do a little rundown of what the last couple of chapters have done for us. So, as just sort of a reminder, chapter 9 focused on solutions, but the important topic there was this idea of molarity, and that's the unit or name that we give for concentration in chemistry. So again, molarity is moles per liter, but that concentration expression or term is what we're going to use for all of the calculations for chapters 10 and 11. All right, chapter 10 focused on kinetics and equilibrium. Equilibrium was really the topic we want to carry through, and what we had to do there is, given a chemical reaction, we needed to be able to write an equilibrium expression. That's basically, if we can ignore the symbols and just remember elementary algebra where we just had A's and X's and B's and squareds and things like that, we follow the rules of math to do whatever we need manipulating those expressions. Oftentimes we don't have to do any manipulation, we just plug numbers in and hit the buttons on the calculator, but sometimes it is important that we can rearrange, find square roots, things like that. And again, focus on that just being a math problem, not a chemistry problem. And we've looked at a couple of examples of problem solving and very briefly looked at some simplifications related to that. All right, the last chapter we care about in this semester is chapter 11, which deals with acids and bases. There's a little nod towards nomenclature. And the nomenclature of acids, we want to recognize that when we have something out front that's a hydrogen, it's probably an acid. And then the names of the acids depend on whether the ending is IDE. For example, HCl in water is hydrochloric acid, so the chlorine gets this hydrochloric acid name. We might also have an ending that is ITE. And the ITE ending, for example, chlorite, which is ClO2. The acid HClO2 would be chlorous acid with an OUS ending. And the other ending we see is ATE. So for example, chlorate is ClO3 single minus. HClO3 would be chlorate. Sorry, HClO3 would be the acid, and that would be called chloric acid. So we see those names, hydro something ic, something us, and something ate. Most chemists, once they start seeing things, they don't even put it together. They just say, oh, HNO3, that's nitric acid. Oh, HClO4, that's perchloric acid, etc., etc. And that's practice. But look over those anion names that are on the polyatomic handout sheet, and there's a little mention there of how acid names work, so recognize that. Bases are usually going to be something that's an ion. So we might have NaOH, and so we see that there. We don't call it an acid, we just say sodium hydroxide, and the overwhelming majority of our bases are going to be hydroxides. We do want to be sure that we're not confusing ourselves and seeing an alcohol and calling that an acid. So this is methanol, this is sodium hydroxide, and the hydroxide is important there. All right, the main reaction for our acid-base chemistry is going to be the neutralization. So H plus OH minus giving us H2O. That is the reaction. But it's often hidden in a molecular reaction. So we might see something like H2SO4 plus LiOH. And what we need to do is recognize, oh look, we have an acid, we have a base, and so one of my products is going to be water, and then we do whatever mental gymnastics we have to, H2SO4, sulfuric acid, LiOH, lithium hydroxide, the H's and the OH give me water, and then I recognize this as maybe a double replacement reaction, and so I'd say, oh, lithium and sulfate must give me LiSO4. There's 2 protons here, so I must need 2 of those, and that gives me 2 waters there. But the driving force of these reactions is the proton of the H plus reacting with the hydroxide to give me H2O. One quick other mention here is that for ease of writing, I usually write H+. A lot of authors like to say, oh, that's really H3O+. Both of these are aqueous. But what this recognizes is that H+ isn't just floating around by itself. It's associated with one or more water molecules. So recognize that's an H++ plus an H2O gives me H3O+. All right, we talked about Ks in the last video. pH involves a little bit of math that usually we address in math classes towards the end of intermediate algebra. pH is a definition, and the pH is defined as the negative common log or the base 10 log of the concentration of hydrogen ions. So you want to be sure you know how to do that on your calculator. There's a couple of ways to do it, but one thing you might do is if you know a value of H+, and you should know its pH. So for example, if we said the concentration of H+ equals 0.01, that could be rewritten as 1 times 10 to the minus 2. If I took the log of this number or this number, they're the same thing, I would get negative 2. So if I had an H+ concentration of 0.01, I'd have the negative there, I'd have a plus 2. So the pH here would be 2. So whatever it is you need to do on your calculator, make sure you can manipulate things around to get that. Okay, so where we need to go now is looking more formally at the use of KW, Ka, and how they apply to both pH calculations, but also calculations involving buffers. So first off, KW is very important. And KW refers to the fact that H2O dissociates reversibly to give me H+ and OH-. All right, what this means is that if I add more hydroxide, so if I add sodium hydroxide to a solution, and here's my beaker of water, and I have some H+, and I have some OH-, and some more H+, and some more OH-, and I add in a bunch of sodium hydroxide, that's going to cause the hydroxide ion concentration to go way up. And what that's going to do is decrease the H+ concentration so that the equilibrium of the KW value is constant. Now, on the surface, maybe this doesn't look like we have electrical neutrality, but remember, I also have sodium ions floating around as spectators. So all those sodium ions take care of the problem of charge being balanced. But the KW doesn't care about that. The KW only expresses itself in terms of hydroxide and H+. So my KW is that the H+ ion concentration times the hydroxide ion concentration is a constant, which is 1.0 times 10 to the minus 14. Okay, if I have just water, it works out that the H+ and the OH- are equal to each other, and so that means that the concentration of concentration H+ equals the concentration of OH-. So it times itself is 10 to the minus 14th, or is equal to the square root of KW, which is the square root of 1 times 10 to the minus 14 is 1 times 10 to the minus 7. So the pH of distilled water is going to be the negative base 10 log of 10 to the minus 7, which is 7. And our general understanding of neutral water is that it has a pH of 7. That's only true at 25 degrees. To truly be neutral, it's just that these two are equal to each other, but the actual concentration varies a little bit on temperature. So as long as they're equal, then we have a neutral solution. Okay, if I were to add sodium hydroxide, so if I said, let's find the concentration in let's just say 1.5 molar NaOH, I kind of use the common ion effect here, but I cut straight to the chase, and I say, oh, well, I know that the hydroxide ion concentration is 0.15 molar, and I know that Kw equals concentration H plus times concentration OH minus. And so if I know this one and I know Kw, then I can solve for H plus, and H plus is going to be equal to Kw over concentration hydroxide. So in this example, that's going to be 1 times 10 to the minus 14 divided by 0.15, which numerically is equal to 6.67 times 10 to the minus 14th. I actually wanted to find pH, so the pH is the negative base 10 log of that number. Again, exactly how that works on the calculator you have at hand varies, but I need to enter that, hit the log button, and recognize I either have to change the sign or just in my head get rid of it. But that would be a 13.18. Quick mention of sig figs. With log math, the sig figs are the things that are to the right of the decimal point. This 13 corresponds to the exponent, so if I had 2 sig figs in my actual data, I'm really only allowed 2 sig figs, or I should have 2 digits to the right of the decimal place. All right, so again, this was an execution of the common ion effect, but once we're comfy with that this will be true and works, we just use this expression. We know Kw, that's a constant, and we either know the H plus because we're given that, if it's a strong acid, or if we're given a base, then we know the OH minus concentration, and we solve for the H plus, and away we go. All right. Lastly, buffers. All right, 2 things about buffers. 1, they resist change in pH. And what that means is if I have a buffered solution and I add a small amount of acid or base to it, the pH doesn't change very much. If I have DI water and I add a couple of drops of hydrochloric acid, the pH will plummet. If I have a properly buffered solution and I add a little bit of hydrochloric acid to it, the pH change will be minuscule, a 1/10 or 100th of a pH unit. All right, so again, that's their operational definition. A buffer is made by combining a weak acid plus the conjugate base of that acid. That's described in the textbook, but sometimes it's a little confusing about how we see that it's a base. So the weak acid is typically something like acetic acid, is a popular one to use, C2H3O2, and the conjugate base is the C2H3O2 minus. But we don't add that by itself, just like we don't add hydroxide to a solution. What we really add is typically a salt of that, and a soluble salt, like sodium acetate. Okay, so I can say that my weak acid is the acetic acid, and my conjugate base is the acetate ion, or I could say the conjugate base is sodium acetate. They're the same thing in solution. Okay, oftentimes we shorten up our handwriting and we just call this guy HA and this guy A minus. Okay, and then we go to the equilibrium expression. And so the equilibrium expression for a weak acid is going to be that my Ka equals the concentration of the H plus, concentration A minus, over the concentration of HA that stays associated. And we did an example before with, I think it was 0.1 molar acetic acid, and said about 99% of the acetic acid stays in the HA form, the combined form. Okay, so if we had a little problem, and it was find the pH of a solution that is 0.10 molar acetic acid and 0.20 molar sodium acetate. How do we do that? So again, what we've got is a combination of the acid and its conjugate base. Okay, there's a couple ways to do this. The textbook chooses to kind of keep the math on the simple side, so we'll do it that way. What we're trying to find first is the concentration of H+, and once we've got that, we just use the definition of pH to solve for the pH. So I'll use this Ka expression and rearrange it to get my H+. So my H+ equals the Ka times concentration HA over A minus. Now, rigorously speaking, I might have to do kind of an icebox approach and see that the common ion effect works here as well, but we don't have to go that far. As long as we kind of trust that the math and the common ion effect works, it works here as well. Okay, so to do this, I'd say that in this particular case for my acetic acid, again, this was all referring to acetic acid, we're going to have that my Ka, I need to know that. The Ka for acetic acid is 1.8 times 10 to the minus 5. That's not something that we would know, it's something we would look up, and I meant to write it up there at the start, but I kind of omitted that. And then I would just multiply that by the other terms. So my HA we said was 0.1 molar, and my HA was 0.2 molar. So my concentration of H plus would be 9 times 10 to the minus, what's that, 6 molar. I think I did that right. Half, so that's 0.9 times 7 minus 5, 9 times 7 minus 6. All right, so there's my concentration of H plus. Again, that was 10 to the minus 6. That didn't show up very well. To go a little further than that and actually calculate my pH, that's going to be the negative base 10 log of that 9 times 10 to the minus 6. Pull out the calculator and I get 5.05. And recognize that's a little bit acidic. My mixture up here was more of the basic form than the acidic form of the acetate. So it'd be a little hard to know if that's a reasonable number, but the pKa of acetic acid is 4.74, and this is a little more basic than that, so it checks out. Okay, the alternate way to do this is using something called the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation is named after a couple of biologists who did some quick math on Buffwrs. And it's basically the same Ka equation. So we start with that Ka equals concentration H plus times concentration A minus over concentration HA. And then we take the P function of both sides. And so we say the pKa equals the P function of this whole thing. And with log math, that means we can break things up a little bit. So this would be the pH plus the P of A minus over HA. Those are concentrations. And if we rearrange that, we can have that the pH equals the pKa minus the P function of concentration A minus over concentration HA. And then for reasons that probably had to do with slide rules and whatnot, we can recognize that we can get rid of the negative p function and just call that a log. But do the same thing, a minus over HA. So anybody that took biology or chemistry more than a couple of years ago would always see this as the equation for calculating pHs of buffered solutions. And it's the same equation, it's just that this is more of a, oops, got rid of that. This is more of a log form than what our textbook uses. But again, pH equals pKa plus log concentration A minus over concentration HA. And this is called the Henderson-Hasselbalch equation. So if I want to do that same calculation, I'd look up the tabulated value of the Ka. So I took the log of the 1.8 times 10 to the minus 5, I get 4.73. If I took the log of this ratio and recognize that this is the log of 0.2 over 0.1, which is 2, I get the same I think it worked out to be 5.03 when I calculated it. 5.03. So somewhere in there I rounded things off a little funny, but it gets the same solution. Again, it should. It's from the same math. All right, so that's that. Other things to study in the chapter would be the Le Chatelier's principle. We talked about that in lab, sort of a qualitative way to understand how reactions work, whereas these calculations would be quantitative, actually figuring out numbers and whatnot. All right, that's enough for now.